Hello everyone, so in this sequence of videos we will go over chapter 5, which is discrete probability distributions. There will be its complement to it, which will be chapter 6, which will be continuous probability distributions. For this chapter we will cover random variables and probability distributions as a in a generalized form. And then we are going to introduce a binomial distribution, the Poisson distribution, hypergeometric distribution, and a multivariate hypergeometric distribution. So what's a random variable and what is a probability distribution? So a random variable, it's an outcome that takes a numerical value, but in this case as a result of making experiments, not as a known value as we usually do with other types of functions, right? We're certain about certain value that belongs to another pair, for example. But in this case, it's a result of undertaking an experiment. For example, a random variable would be some days, for example, as written in the text right here, tomorrow's high temperature. So what are we going to do in this case? So we are going to take temperature at different times and record all throughout the day. And then we are going to identify the maximum value, which will be the highest temperature of the day. Again, for random variables, keep in mind that we have two types of data. Remember chapter 1. So let's go back and refresh just real quick our definitions from chapter 1. Well, so we are going to have discrete and continuous discrete random variables. So let's highlight. So something it's not working very well here, I guess. I think it's my pen. Let's see, give me a second here. Don't tell me this is not working. Okay, so we are going to have infinitely many values for a continuous random variable, as opposed to discrete random variables in which we just look at countable values, right? Like, for example, the number of eggs of a hen, for example, it's just 1, 2, 3, 4, 5, or the number of times we roll a die, for example, we roll it once, twice, 3 times, etc., but we don't roll it half a time. That doesn't make sense. And back to continuous random variables. Well, in this case, we consider the infinitely many values within an interval, for example, temperatures, in which we include not only the integer values, but also decimal values, for example, 50 degrees, 51 degrees, 51.53 degrees, 55.79 degrees. In this case, we include decimals as well. Okay, so let me just see what is going on with this variable, with this. Okay, hopefully, yes, it's working. So continuous random variables, infinitely many values. Discrete random variables, finite number of values, or countable number of values. Okay, so what are probability distributions? So how can we define what are they? So in this case, okay, let's compare and contrast chapter 4, which we did before this chapter, in which we cover probability, different rules, conditional probability, independent events, dependent events, mutually exclusive, etc., addition rules. So we went over different situations that model probability calculations. However, in those situations, we were certain about the outcomes and of the situations. However, in this case, we are going to do the following. We are going to describe what will probably happen as opposed to what actually did happen. Okay, you will see the difference when we look at some examples and some situations. Also, what is this? What is the relation with other chapter 2, in which we went over graphs? Remember, we went over pie charts, frequency distributions, bar charts. So those histograms and those bar charts were using observed sample values that actually were collected. Okay, but in this chapter we will construct probability distributions by presenting possible outcomes along with the relative frequencies that we expect. Okay, so what is the difference? So in chapter 2 we work with data that was already collected. Here we are going to kind of model situations and predict based on certain on certain specifications of a situation. For example, the binomial distribution will have its characteristics, the Poisson distribution will have its other characteristic that we will describe in gory detail later in the chapter. Okay, what are the properties of a distribution? Okay, so the random variable number one is represented by x, some value that the distribution will take, right? And it's a single numerical value. Okay, and a probability distribution, well, it can be presented in the form of a graph, in the form of a table, and in the form of a formula. That'll give us all the possible outcomes. Okay, as we defined in the previous chapter, the sum of all the probabilities will have to be 1. Otherwise, if you're given a data set and they ask you, oh, determine whether this is a probability distribution, you will add all the given probabilities and make sure it adds up to 1. If not, well, then that is not a probability distribution. And each probability in the distribution has to be between 0 and 1. For example, 0.3, 0.5, 0.7, and then add them all up to get 1 as a probability, as a total probability. Okay, what is the vocabulary that we are going to use in this chapter? Okay, this new term, expected value. Expected value, it's just another fancy way to say mean. Not really a fancy way, because the mean, it's something in the previous chapters. I'm talking about chapter 3, in which we learn how to calculate the mean in different situations. The arithmetic mean, in which we just added the number of all the given values and divide by the number of values, and then the mean of a frequency distribution and the weighted mean, etc. So we did the mean of a grouped probability distribution. So we did many different mean calculations. However, in this case, the expected value, it's pretty much the same as the mean. However, we call it expected value because in this case, as we mentioned in the previous page, a couple minutes ago, we are using probability distributions to estimate what will probably happen. In this case, what are we expecting? So the mean now takes a different name, expected value. Nevertheless, we are going to be referring, I will be using both words in our vocabulary as we go through the videos, as we go through the lecture. So let's say other ways to call this expected value. If you read other textbooks, you may, or other resources, other videos, you may find this as expectation or mathematical expectation. Okay, so, and this is very, very important in order to, when it comes to applications that have to do with decision theory. Okay, so for example, for those of you who are going to go to a business major, a lot of these probability distributions are going to be very, very useful for you. More like how this works. What's pretty much the lingo, the do's and don'ts. So here we have more properties, rather more like properties. I would say these are the formulas, right? The formulas are for the expected value. It's the sum of the product between the x, which is the random variable, times its probabilities, which in this case is, okay, let's see, let's change colors right here. So this is the calculation for the expected value. And in this, notice, see the note, notice E, which is the expected value, is the mu, which is the mean. So it's basically the same thing. However, we just refer to it in a different way. Variance and standard deviation. The standard deviation, again, keep in mind it's the square root of the variance. And we get it by adding the product of the random variable squared times their corresponding probabilities and subtract the mean square. So I mean, right now they look like just formulas. We are going to make more sense about this when we go over the numerical example, which is a couple of numerical examples which are in the following pages. So calculations for the round off rule. So in this case, we are going to round to one more decimal place than the number of decimal places used for the random variable x. All right, for example, if we are given all integers, our calculations will be rounded to one decimal place. If we are given values with 3 decimal places, our rounding will be to 4 decimal places. So it's always one more than the given. So let's see. Let's look at one example. So suppose we toss a coin so that the sample space is, tossed twice actually. It's tossed twice in a way that our sample space is head heads, head tail, tail head, and tail tail. Right? Those are the possible outcomes for tossing a coin. So in this case, let x represent the number of heads. So in this case, the big X right here will be the random variable. This random variable, which will be the number of heads that can come up. We could have defined otherwise the number of tails, but in this case, we decide to let X be the number of heads that come up. So we are going to develop a probability distribution for the random variable x and find the expected value and the standard deviation of the distribution. Okay? All right. So let's write down what random variable will be. So x will be the number of heads. So if we perform this experiment twice, by the way, I forgot the word twice. If we perform if I toss a coin twice, the possible outcomes I get 0 heads or 1 head, or maybe I run lucky and I get the 2 heads. All right, let's see. So this is where we are going to write down. So either 0 heads, 1 head, or 2 heads. Okay, now notice the sample space is given in 4 possible outcomes. So in this case, we are going to assume that the coin is a fair coin, right? So in this case, we had the chances of getting the head 50, tail 50. So it's a 50-50 coin. Of course, there's a lot of fraudulent people who like playing those coins, and then you don't realize that maybe the coin has 2 heads, and if you decide tail, you never get the tail, right? Or maybe the coin is it's built in a way that it always lands heads or tails. So in this case, we're going to assume a fair coin. And each outcome right here will have a probability of 1/4, 1/4, and 1/4, and 1/4. Okay, now, so let's look at the probability. Okay, so let's develop the probability distribution. So I'm going to find the probability of getting x equals 0 heads. Okay, if we look at, in this case, if we look at, let me erase this blue right here. I'm going to highlight this with yellow. So in how many possibilities do we get 0 heads? Do you notice it's only one possible in the sequence tail, I don't get any heads. So in this case, we get that by looking at the probability to get 2 tails, which in this case is 1/4. Right? Now let's look at the probability to get x equals 1 head. Okay, in this case, okay, let me use a different color to highlight this. I'm going to use blue. Okay, x equals 1, we get x equals 1 by getting the sequence head tailed and tail head, in this case 2 of the outcomes. All right, so let's use actually the probability notation. So the probability of getting either head, tail, union, that's the OR symbol, remember from last chapter, tail, head, which is the same as just adding the probability to get head, tail, plus a probability of getting tail, head, which in this case is 1/4 plus 1/4, which reduces to 1/2. Okay, by the way, let's start writing these probabilities. I get 1/4, I get 1/2. Now let's look at the third probability, the probability to get x equals 2 heads. I'm going to use orange. How do we get 2 tails? Do you see there's only one outcome? Head, head. Let me actually use a different color so it doesn't get confused with the orange. So let me x equals 2. And in this case, there's only one probability of head, head, which in this case is only 1/4. Okay? Now, let's write that 1/4 right here. One thing to make sure here is that if you add these 3 values, the sum should be equal to 1, as we can tell. Okay? Now, in the next column right here, we are going to multiply these two numbers, column 0 times 1/4. So 0 times 1/4, which will give us 0, 1 times 1/2, which will give us 1/2, and 2 times 1/4, which will give us 1/2. Okay? And let's add this up, add these numbers up to get sigma, the summation, to be equal to 1. Okay, and then we are going to fill in the last column by multiplying the square of x, which is 0 squared, 1 squared, 2 squared, times 1/4, 1/2, and 1/4. If we multiply each of these, we get 0, 1/2, and 1. If we add this together, we get the sum to be 3/2. All right, now, how are we going to use these calculations that we just did? Well, we're going to use this to calculate the expected value E. Okay, so the expected value or the mean, which is E, will be the sum of the product of x's times its probabilities, which actually happens to be this third column right here. So that's why I did these calculations. Okay, let me highlight so you can relate this. So x times p for each is x times p over here as well. And the sum will be 1. So that is the expected value. I will show you in a picture what is that going to mean. Okay, so the other piece of information is to calculate the standard deviation, which is the square root of the summation, the sum of x squared p of x minus the mean squared, which is no other than the expected value squared. Okay, and as you can notice here, that's why I did this x squared times p of x, which is the summation right there, the one I just highlighted. So x squared times p of x, whose value is square root of 3/2 minus the expected value quantity squared. Okay, and in this case, if you simplify this, you should get the square root of 3/2 minus 1, which is the square root of 1/2, or square root of 2 over 2. Okay, we can leave it like this. Okay, what does that mean? Let's see. So let me do a couple of graphs here. So, for example, okay, let me use green here. Okay, so that's 0, that's 1, and that's a 2. And over here, I'm going to have 1/4 and 1/2. Okay, so I'm going to draw a distribution for the number of heads. In this case, for 0, what is the probability of getting 0 heads? The probability is 1/4. I'm going to draw just a line. What is the probability of getting 1 tail? In this case, the probability for getting 1 tail is 1/2. Okay, so I'm going to go all the way here. And what is the probability of hitting 2 tails? Again, that gets reduced to 1/4 again. So if we look at this as a distribution, for example, you might remember the bell curves, remember? So it would look roughly like this, right? So, in which the average, the mean, which is going to be the value which is in the middle, which happens to be 1. So that means that in this case, we translate this as the fact that we are most likely to get 1 tail, because that's the instance that repeats the most. It would be kind of unusual to get 2 heads. I mean, it's possible, but not not as likely as getting only 1 head. If you view this as a bar chart. Let me do another chart right here. So I'm going to do a couple of bars here, and that's going to be 0. This is 1, and this is 2. Okay, so let me do the graph. Oh, this is going to be still, again, 1/4 and 1/2. Just for you to have a better picture of this. So probability for 0, the probability for okay, I don't think that worked. Let me fix this real quick and one more. See, again, do you see that it is most likely for us to get one tail? That's what the expected value means in this case. Okay, let's look at another example, and then this is typically this is a very typical example in when it comes to introduce probability distribution. An example like this help us in a way, if you will, to make money. To see, for example, let's say you want to do a game at a fair, and you want, of course, you want to make money, and then you will design a game like the one below. So let's see. So a die is rolled in a game with the prices described below. If the die lands on an even number, the player loses $4. If the die lands on the number 3, the player stays the same, doesn't win, doesn't lose. All right. And finally, if the die lands on 1 or 5, the player wins $5. I mean, if you look at this, looks like a fair game. All right. So the player would give it a try or a few tries. Okay, but let's analyze what's going to happen in the long run. Will you make money as the owner of the game, or will the game will be poorly designed in a way that the player wins all the time? That's an example in which the expected value will tell us whether we make a decision to go with this game, right? Remember, we in the previous couple pages we went over with the fact that these probability distributions help us in decision theory. Of course, I was talking about in more serious and in the finance area, the stock market, for example. But I mean, I guess this simple game right here, it's going to give us an overview of how knowing some of statistics will help determine whether we can make money or maybe not. Okay, so let's develop a probability distribution for the random variable x and find expected value and the standard deviation of the distribution. Okay, so let x be the random variable, which will be the economic result. Okay, the economic result. Okay, so what are the impacts? What are the values of the random variable in this case? Right, so let's highlight the first sentence. If a die lands on an even number, the player loses $4. Okay, so let's see. Number 1 is to lose $4. Second sentence, if the die lands on a 3, the player stays the same, doesn't win, doesn't lose. Okay, so 0, nothing. And finally, if the die lands on 1 or 5, the player wins $5. Okay, so $5. So those are the three possible, the values that the random variable takes. Okay, so number one, it would be a good idea to define our sample space with the sample find fancy S. Okay, so the sample space will be described as follows. So we can roll a die and get a 1, get a 2, get a 3, get a 4, get a 5, and get a 6. Okay, again, if this die was manufactured fairly, each possible outcome will have the same probability to occur. In other words, each probability right here will be 1/6, 1/6, 1/6, 1/6, 1/6, and another 6. Okay. All right, so we are going to find the probabilities here. So it's not going to be just putting any fractions. It's going to be a process that I'm about to explain here. Okay, so we are going to look for the probability to get the random variable x equals -4. So how likely are we to lose $4? Okay. So how likely are we? In this case, the probability of losing $4 happens if the die lands on an even number. That is, if we land on a 2, if we land on a 4, or if we land on a 6. All right? So let's use the notation, the correct notation from probability. So the probability of landing at 2, union landing at 4, union at 6, which will be expanded as the probability of hitting a 2 plus the probability of hitting a 4, and well, not hitting, rather landing, having the die landing on 6. Okay, so this will be 1/6 plus 1/6 plus 1/6. Okay, this will be 3/6, which reduces to 1/2. Okay, so let's record that probability over here. Now let's look at the probability of having a random variable to not getting anything, neither lose nor win. And that happens only when the die lands on a 3. Okay, and in this case, well, it's only 1. So let's denote it using the correct notation. So the probability of hitting a 3, that's the only possible outcome that will make us neither win nor lose. And in this case, is 1/6. So let's record it right here. And finally, let's find the probability of winning $5 in the game, right? So in this case, that is possible if our die lands a 1 or a 5. And this will be the probability of hitting a 1 or a 5. Remember, the union symbol from set theory indicates the OR. And in terms of probability, we add the probabilities. And the probability of landing a 1 is 1/6, plus the probability of landing a 5 is another 6, which reduces to 2/6, and which adds up to 2/6, and reduces to 1/3. Okay. Now, if we add these three numbers right here, this should add up to 1, as you can tell. Otherwise, your calculations may not be correct when you do the calculations I did below. Okay, so now let's obtain the two additional columns to calculate both the mean and the standard deviation of this. Okay, so let's see. So we multiply -4 times 1/2 to obtain a -2. We multiply 0 times 1/6 to get a 0. We multiply 5 times a third to get a 5/3. And in this case, the addition of all these numbers will be -1/3. Okay, this number is good. If you are the person designing the game, it's good. I'll tell you why when we analyze this in a graph. Okay, the next part will be to -4 to multiply the squares of the random variables times their probabilities. So we get 8 for the first case, 0 squared times 1/2, still 0, and 5 squared times 1/2, no, not 1/2, I believe it was a third. A third, and this was supposed to be a sixth. Okay, give me a second to correct this, all right? So 1/6. That equals to 25 thirds. Okay, so we are going to use these two columns, the third one for calculating the expected value, and the last one to calculate the standard deviation. Okay, so if we add these numbers together, we should get 49 thirds. All right, let's look at, let's go with the calculations of, okay, what colors did I use? Okay, blue. With the calculations of the mean. I mean, or expected value. Well, it's still correct to say the mean, but again, in this vocabulary here for distributions, we call it expected value. It's more properly speaking. So expected value will be x p of x, the sum of them, which we got it here. Okay, that is -1/3. And lastly, well, almost lastly, the standard deviation, which will be the square root of the sum of the random variable squareds times the probability of each possible outcomes, right? So, and I almost forget to subtract the mean squared. Okay, so we are going to get the square root of the sum with this sum right here corresponds to all this, which is 49 over 3 minus -1/3 squared. Okay, so if we simplify this, I'm gonna get 146. I'm just gonna skip a few steps here. You do the rest in your calculator. I get the square root of 146 ninths, which simplifies to 4.027. But again, basically 4.0 because we're given integers as data, so we have to round to the nearest, in this case, 1 decimal place. Okay, now what is this going to mean? Okay, here we are going to connect, we're also going to connect vocabulary from chapter 3. Remember the mode? Okay, you will see. So let me draw a line here, and let me do another graph, and let me do a vertical line divided into 1, 2, 3, 4, 5, 6. Each line will represent 1/6. In this case, I'm going to have the 1/6 2 6, which is 1/3, and then 1/2. Okay. Now let's see. Let's label 1, 2, 3, 4, 5, 6, 7, -1, -2, -3, -4, -5, -6. Okay, let's leave it to -6. 1, 2, 3, 4, 5, 6, 7. -1, -2, -3, -4, -5, and -6. Okay, so I'm going to draw a bar for the probability of getting, of actually losing $4 in the game, which in this case is 1/2. Okay, I'm gonna do a bar for losing let me do this bar. Then I'm gonna draw a bar for staying the same, that is 1/6. So 0, 1/6. And finally, the probability of winning $5, which is 1/3. All right. Now let's look at this bar chart. Let's look at this as a distribution. Okay. Notice this distribution is sort of skewed to the right. Okay, that is we're smashing a little bit from, and at the same time it's kind of skewed to the left. Okay, so let me use a different color, some color that contrast. Okay, black. Okay, we're gonna get this. Do you see these two humps right here? The graph has. Remember the term bimodal? In a way, it looks like a little bit like a bimodal distribution. However, its mean seems to be somewhere here, which corresponds to the -1/3. Okay, why is this good for you as the designer of the game? Well, that means that the player will lose, is most likely to lose money. Okay, so in this case, suppose, just so you get an idea of how much money you would expect to make. For example, let's say you perform this game, do this game 500 times. So multiply 500 times -1/3. Okay, and if we do that, okay, let's calculate that. Let me use my calculator here. So when I multiply, where's my calculator? Right here. 500 times -1/3. So around $166 with 66 cents. That is most likely, that is the expected amount of money that you would make. Okay, so this is the importance of understanding expected value, how it works. So next time you play a game like this, you now have the basics of how to understand the game. Is it a fair game? Is it sort of a game? I mean, this -1/3, well, it doesn't look that harmful, right? However, if the expected value fell like over here, okay, fell like over here, let's say $2.5, to lose $2.5. So again, this expected value is, it means that in the long run, yeah, I wanted to explain that earlier, but I couldn't find the words to put it. average, a player would be losing 1/3 of a dollar, which is basically 33 cents, right? In average, right? In the long run, after a repeated number of times that this process is performed. It doesn't mean that because in the game description it never says to lose 33 cents, right? It doesn't say that. And I mean, here the process in the long run, it doesn't seem like much, but in the long run, if you perform this game 500 times, it is most likely that you would make $166. Of course, for example, people will run lucky. Maybe people would get, maybe there will be people who get this, who loses 4 or wins 5, etc. Okay, so this is a general overview about probability distribution. In the next video, we are going to go over the first type of distribution, the binomial distribution. See you there.